Well, good to see you back again. So, with that, we're actually going to skip ahead to chapter 12 with that. So we're going to do chapter 12 and chapter 13, and then come back to chapter 11 with that. So the chapter 12 is the 13 are dealing with structural information. So how do you get, how do you figure out what you have in your flask after you do the reaction? So with that. So these are going to be the techniques that we're going to be dealing with for the next two chapters. We'll come back to chapter 11. That's a reaction chapter, and then move forward from there. So with that. So there's four main techniques that we're going to be learning about. With that. So mass spectrometry and infrared spectroscopy are the first two. Then we'll hit NMR, nuclear magnetic resonance spectroscopy, in chapter 13, and then ultraviolet spectroscopy comes up, I believe, in chapter 14. So that's pretty short. So but really, so for mass spectrometry, what you're going to be using that for is to figure out how much your compound weighs. So that's its molecular mass, and from that you can estimate the chemical formula. Infrared spectroscopy, it's usually primarily used to look at the functional groups. So each functional group has its own sort of fingerprint, and so you can use IR to do that. UV spectroscopy, that's used for the presence of conjugated pi electron systems. So the more sort of like double single bonds that you've got, the longer wavelengths of light that you can that will absorb. So the more red something is. And so NMR is going to be in chapter 13. That's really understanding the framework, particularly the carbon framework and the carbon-hydrogen framework. So that's looking at the nucleuses and how they are packed together. So arrange that. I will warn you that chapter 13 is a little weird, but it's not hard. So it's just a little bit. But before we do that, we're going to talk about mass spectrometry and infrared spectroscopy. Okay, so mass spectrometry is all about, as the name implies, measuring the mass, stuff like that. And so what we want to be able to do is if we can get the mass, we can estimate the weight, and from the mass, weight, and then chemical formula, stuff like that. So first, there's actually three steps for mass spec. The first one is to ionize the source. Well, so you inject your sample. You have to actually be able to get it into the gas phase, stuff like that. And from there, we're gonna be able to. Going to want to do is put a positive charge on it, and then it's attracted. And then at the end of our instrument, we're going to put a negative charge, and it'll get attracted to it. From there, after we put the charge on it, you'll have a mass analyzer, which sounds impressive, but really all it's doing is separating the molecules that have been charged by their mass. So that, and specifically their mass to charge ratio. Most of the time, you're going to have it's just going to have a +1 charge, so like that, and so it makes the mass work pretty well. But if something actually has a +2 charge, it's actually going to fly twice as fast. So you have to account for that. So it's technically the mass to charge ratio. But for pretty much what we're doing here is we're just going to assume that it's a +1 charge, and to make life easy for you. And then at the end, what we're going to do is we'll have a detector at the end, and so you can sort of see how many of each mass size is coming and hitting, stuff like that. And literally, what you're doing is you're counting how many strikes, how many masses of 100 are there, or 101, or 102, or 103, and you'll get this, and that's what you're looking for at the end, is how many times for that particular mass the counter it hits the detector, stuff like that. So the way that we get the we make the molecule have a positive charge, stuff like that. So this is probably an older method, so that it still works, but it's, and we'll see it can be somewhat problematic. With that, and so it's what's called electron impact ionization. So with that, and so what you do is you eject your sample, and then you throw high energy electrons at the system. And what that does is that the electron, right, an electron within your molecule is actually going to get repulsed by this high energy electron. It's going to get knocked away, stuff like that. And so what happens is if you knock an electron away from your molecule, right, it's deficient in one negative charge, so that gives it a positive charge, stuff like that. So this works out for for small molecules. It works pretty well up to about 2500 AMU, but it's a pretty harsh way of giving it a positive charge, stuff like that. And so after right, so here we go. So right in here, that's where the molecule gets heated, put into this gas phase. It goes in, gets bombarded by electrons, and then gets pulled down down this tube basically, which is has a negative charge to it. Comes down here, goes through a slit to make sure that it's just polarized, going the right way, and then it gets bent by this magnet and stuff like that. And so it's sort of, you can sort of think of it as sort of like a go-kart can make this corner really fast because it's very lightweight, but a big old semi truck, right? It's going to take a lot longer to make that corner, and so it's going to get deflected not nearly as much, and so the heavier stuff won't get bent as much as the lighter stuff. And so this traveling down the tube and this bending effect is what's going to separate out the charges, so like that, into there. And you have a detector in here, and so you have different places for each charge, so like that, and you just count how much is going through where, like that. So so that's the typical instrument setup, so like that. And so what ends up happening is you get the spectrum here, and you have a detector for each molecular mass, right? And you just count how many strikes you get at each weight, so by that. And so don't forget, you're always looking at the mass to charge ratio. Again, we're going to assume that it's +1. There's two things to note. One's the base peak, which is just whatever goes to 100%, right? The highest peak. Typically, that's not going to be what's called your parent ion, which is the highest molecular mass peak. That is actually the most important one, and it's going to be your mass with a plus charge, right? So in this case, our compound has a weight of 44 AMU with that. So but typically, it's your parent ion is not going to be your base peak like that. So the parent ion is the one that's really, really important here. Okay, and so right here, he's just saying 44. The problem is what you're looking at in the mass spectrum is not the average, right? So you think of carbon as being, you look at the periodic table, it's 12.01 or whatever it is, and hydrogen is 1.007, stuff like that, right? But or 1.01, I think it is, stuff like that. Well, as it turns out, what you're actually looking at in the periodic table is the exact mass, and so carbon's going to be 12, hydrogen's going to be 1, and things like that. Nitrogen's going to be 14, oxygen 16, stuff like that. We're not talking about the weighted average of the periodic table. We're talking about exact mass, and so those masses are going to be a little different. They're going to be close, but they're going to be a little off, and stuff like that. And so if you notice over here, we talked about the parent ion being here. You notice that there is a small peak, just one higher than that. From that is actually going to be those side peaks are going to be those naturally occurring carbon-13 deuterium molecules that weigh. It's going to make the mass be 1 larger, but it's just only 1 or 2%, right, of those of that peak, stuff like that. So it's going to be a very, very small peak, stuff like that. So most of it's going to be this main peak, and then you're going to have some isotopes on either side, isotope-containing compounds, just naturally occurring, stuff like that. So okay, so the nice thing is let's say you have 72. You say you put your sample in there and you get a mass of 72. The problem is, you could have this as C5H12. If you add that up, that becomes 72, or C4H8O. That also has a 72. So how are we able to determine the difference between the two if we only had a mass spec and stuff like that? And so what we do is we actually increase the number. We get higher resolution. And so we put additional, you put in an instrument that has a lot more decimal places. And the fact that there is slight differences between, hydrogen and oxygen, if you go out enough spaces, right? So these guys here, you can account for those slight differences in mass. If we're going to set carbon at 12, right? You can tell the difference between the two, right? So if we put it in there where we don't have any decimal places of 72, we're not going to be able to tell. But if we get in here and we get an instrument that has 4 decimal places, we can tell, if we scored our sample in the one instrument, said 72, but it comes out at 72.09, we know that it's actually this one here and not that one. So that's one of the ways that you can tell between the two compounds. Now, there are times where there is no parent ion, or I should say that the parent ion is not the M+. Right? So if we put in 2,2-dimethylpropane in here, it's a molecular weight of 72. Right? We should see a peak here, but we're not. What's happening is it's breaking. The molecule's fragmenting too much before it gets down to the detector, and stuff like that. And so what you guys have to do is you have to go to a reference standard and put in these main peaks, and lots of times they'll fragment in a particular way, stuff like that. And so that fingerprint way of that unique way of fragmenting is a fingerprint that you can look up for node spectrum, stuff like that. But the stuff I'm going to make you guys do, we're always going to have an M+ peak. Okay, so why does this happen, right? So why do sometimes we not have the proper parent ion? Well, the problem is, right, so when you hit this with an electron, knock this off, what you're doing is you're taking a 2-electron bond and turning it into a 1-electron bond. And so it's going to be fragile, right? So that it can very easily snap when you when you put it going down here. And so it does take some time to get down to the detector. And when doing so, the molecule can fragment away, right? So if we chop off, this ethyl group here, we would be left with this, going from 1, 2, 3, 4, 5, from 6-part to a 5-part piece, right? So this part just fell away, right? And we'd be left with this with a plus charge. Or if the propyl part fell away, right, we'd be left with a 3-electron piece. If 4 parts fell away, we'd be that. 1 part fell away, would be this, right? So it's going to be you're making the molecule itself unstable because you're slicing, you're taking away half of the glue holding together the molecule, and so it's easily broken. Now, I'm not going to make you do the predict the fragmentation pattern. I don't think it's helpful in this class. If you want to take I think it's helpful in the analytical chemistry class because they're going to be much better about being able to determine it. But I just want to let you know that it does happen, but I'm not going to make you determine it. So like that. So because the way that it breaks, it actually, you see this over and over again how it breaks, right? So you get what's called alpha cleavage, which particularly if it's next to a heteroatom, it can happen. So if you break here, what can happen is you can, if it breaks there, you get a carbon plus, but your lone pairs can come down to make to give the octet on the carbon, right? So you can get a lot of alpha cleavage. You can also, if it breaks, you can also get dehydration, right? Because making a water molecule is really stable, right? So it can dehydrate and make the molecule more stable. Like that. So again, alpha cleavage with the means because you can come down and have these lone pairs come down here to to help out this carbon plus, right? So you can just lop that off, that part off. Carbonyls, again, you can get these alpha cleavages. We cut off part of it there because it can get stabilized. So by that, you can also have what are called McLafferty rearrangements where things sort of cyclize around and so make things a little more stable. So with that, but again, it's one of those things to know, but I'm not going to make you predict what the rearrangement is going to look like. Okay, another weird, quirky thing about the M+ electron ionization is what's called the nitrogen rule. Turns out that it just works with nitrogens, mainly, I should say. So if you have an odd M+, what that means is you have an odd number of odd number of nitrogen atoms in your molecule. So if you have a 73, that means you have either 1 or 3 or 5 nitrogens in it. Now, if you have an even number of nitrogens, that means you have an even. If you have an even M+, that means you could have nitrogens. You just have an even number of them. So like that. So do be careful if you ever see an M+ that has a negative number, odd number, then you at least have 1 nitrogen in there. So, okay, another thing to remember, this is coming back from chapter 7, we're going to be using this a lot over the next couple of chapters, or this chapter next, is this degree of unsaturation, right? So you can use this equation. It works pretty well. So with that, I'm going to give you the equation. I'm not necessarily going to give you the key, but I'll give you the equation, right? So 2 times the number of carbons plus 2 plus the number of nitrogens minus the total number of halides minus hydrogens, all that divided by 2. And that number that you get out is going to be the number of pi bonds and rings, right? So with that, so don't forget about that. The other thing that you're going to want to think about, and this is how I solve these problems, is think about what a completely saturated hydrocarbon is supposed to look like. If you count this out, for every carbon, there's 2n plus 2 hydrogens that could be attached to it. Right? So a fully saturated carbon, what's the maximum number of hydrogens you can get? You can have attached to that. Right? So that means it's the biggest it could be. Right? So if it's, so C4, right? How many potential? What's the maximum number of hydrogens we can get? Well, it's 2 times 4 plus 2. Right? So it's 10. Right? So the maximum saturated C4 compound is going to be C4H10, right? So if we have C10, right, what's the maximum hydrogens that we can get? Right, it's 2 times 10 plus 2, right, so it'd be 22. So we see C10, C10H22. Okay, so this is the heaviest it could be, right? So that's the most hydrogens you could have on there. Okay. Okay. So with that, so how do we do this, right? So how do we say what's the determine the structure? Okay. So we have. So here we go. Okay. So here we go. Now I'm going to tell you that it's a hydrocarbon, right? So with that. So what does that mean, right? So this means that this is C plus H, right? So with that, so carbon, right? That's all we've got. Right, so that means that this mass here is always just C plus H. Okay, and so we're going to figure out, we got to figure out how many carbons, how many hydrogens to do it. So the way that I do this is we say, okay, we come in here and we say, okay, so let's say there's, I don't know, we got to start somewhere. So let's say there's 9 carbons here. Okay, so what's the max number of hydrogens we had? We could have if we have right, if we had 9 carbons, right? So it would be 2 times 9 plus 2, right? So that would be what, 20? So that means that, right? So we could have C9H20, which if we did that molecular mass, right, it'd be 9 times 12, right? 9 plus 20 times 1, right? So we have 20 hydrogens each one. We have 9 carbons, each one is 12, and so the maximum that you can have, right, is 128 AMU. Okay, we can't stuff more hydrogens on here to make 132. This is the maximum it could be. Okay, so that means you're probably going to have 10 carbons. Okay, so what's the maximum number of hydrogens, right? Well, it's 2 times 10 plus 2, right? So it would be 22. So that means it would be C9H22. Oh, excuse me, C10. C10H22, right? Which 10 times 12 plus 22 times 1, right? So that would be what? 142 AMU. Okay. But, right, so we can't have 9, right? Well, we have 10, right? But how do we get from 1? That's the maximum it could be. Right, but ours is 132. So the easiest thing to do is to say, okay, let's reduce this down. Let's say remove, right? We're going to move 10 hydrogen atoms. Okay, so that means that the formula is going to be C10H12. Okay, so if you want to double check, right? So 10 times 12 plus 12 times 1, right? So 120 plus 12 is 132. And so here's our formula. Okay, now, where did I get these numbers from? I just guessed, right? So there was a 132, so it's probably going to be a fair number of carbons in there, so let's try something. right? And if this number gets above it, so you really, the best way to do it is to frame this, right? Be one below, above, and so now you've got a good shot of knowing where it is, right? One below, one above, right? So it's going to be between these two. So you can note, well, I know I have 10 carbons and I can remove it, right? I can't add hydrogens here, right? Because this is the biggest it could be. You know, otherwise you're going to start having carbons with 5 bonds on it, which you obviously can't do. Stuff like that. So you have to go one carbon larger and then remove hydrogens. Now, that's not the question. The question was not, what's the formula? The question was, what's the structure, right? So from here, what we do is we say, okay, we're going to use that DOU equation, right? So DOU is equal to what? So it's 2 times number of carbons, which is 10, plus 2, right? There's no hydrogens, right? There's no halides, right? But there is 12 hydrogens. Oop, that's a minus. All divided by 2, right? So it'd be 22 minus 12, 2, which is 10 divided by 2, which is 5. Okay? I forgot to show you this, right? There's that. So this is equal to what? Pi bonds plus rings. Okay? Now I have given you, that's all the information I've gotten from you is this. And so all you would need to do is figure out some combination of rings and pi bonds that equals to 5, right? But I haven't given you any of the information, so you can do whatever you want, right? You could do 2 rings and 3, you can do 2 rings and 3 pi bonds, 4 rings and 1 pi bond, 1 ring and 4 pi bonds, right? You could do, it's what, C10, 2, 4, 6, 8, like that. You could do, no rings and 5 pi bonds, right? You could also do, don't forget, right, 2, 4, 6, 8, 2, 4, 6, 8, 10. You could also do a triple bond, right? That's worth 2, right? So you get 2, 4, 6, 8, 10, right? You could put them wherever you wanted to. That would work. I haven't given you any other information than that, than the fact that the formula is here is that, so you can do whatever you want, stuff like that. So as long as it makes sense, you can do whatever you need to. Okay, so it's whatever combination of that. Now, eventually, I'm going to give you additional information, additional criteria for doing the structure, but for right now, and so there you have to follow, it has to make sense to what you're seeing here. Okay, so like that. So, okay. Now the other thing you have to do is figure out. And this will come up, and I don't have an example for this, but let's say instead he says M plus is 132, and I said, oh hey, there's an alcohol in here, right? And so, right, the alcohol is going to be an OH, right? So what that means is, right, so C plus H plus O is 132, okay? And so what you're going to have to do to just separate that, right, the C plus H is going to be 32 minus the weight of the oxygen, right? So it's going to be 132 minus 16, right? So it'd be what, 116, right? So C plus H is going to be 116, right? So then you go through this process here of figuring it out, okay? But then let's say it's, for, I don't know what it is, but let's say it's C9H, 15, right? That's what this is. I'm just making this up. I don't know what it is. The final formula is going to be that C9H15O, right? So that's what the formula would be. I'm just making this up on the spot, so these numbers are wrong. Something like that. But the final formula would be that. Okay. So if I tell you that there's some sort of functional group that says it has a heteroatom, like an oxygen or a nitrogen, you have to account for that in here, that what you're solving for here is the total number, but in order to do this process here, you can only do the hydrocarbon piece. So you're gonna have to subtract that part out, okay, do the hydrocarbon piece, and then put that oxygen back in, okay? So be careful. Okay, so for mass spectrometry, right, they're going to be, most molecules are going to be larger than 25 AMU. But also, you don't want to, you want to try to keep those samples from fragmenting, right? It's kind of a pain in the neck when they fragment. So what they've done is they've actually developed two other methods that are much softer. One is called Electrospray ionization, and the other one is called matrix assistance laser desorption ionization, or what everybody calls MALDI. Okay, these are going to be much softer, much less prone to fragmentation. And so what they do is they still so for Electrospray you still have to put it still goes into the gas phase, but instead of hitting it with electron, what you do is you just add a hydrogen ion, right, an H+, and so it has an extra H+ associated with it. You end up that gets the positive charge. It's going to be a much softer way of getting the it's just a simple acid-base chemistry. It's going to be a much softer way of getting that a positive charge on that ion. Now you do have to be careful, right, because you're not getting an M+, then you're getting an M. What essentially is an M+1 charge, right? So if your sample, so if you put in Electrospray, your sample is 100 AMU. When you the parent ion that you get out is going to be 101 because now you put an extra hydrogen on it, right? So you have to be careful with that. So, okay, same thing happens with the with MALDI, right? You put a hydrogen on there with that, and so and so you're going to get an M+1 charge instead of the M+. Okay, but the problem with the way this works is that if you're going to be having it, what is it? This is for really big samples that couldn't possibly get into the gas phase normally. And so what you do is you strike it with a laser. It's really cool. Put it on a gold plate. You hit your sample with you put the sample on there, let it dry, and then you strike it with a laser, and then that sort of blows enough of that sample up into the gas phase. So with that to be able to detect it, right? So with that, so and you actually have a matrix compound which helps that along, so with that, and so but the lasers make everything better. So with that, so this is a really cool method to do. With that, you need very little sample to be able to do this. But the nice thing is, and then the other thing they do is instead of having this bend tube, stuff like that, so what they do is they have a very accurate clock. And so they know exactly how long the tube is, and then they have a very accurate clock. And so what they can do is they can tell that things that are smaller, right, they're going to travel faster, right? They just have travel faster, and so like that. And so they can time when those how long the sample takes to get to it. And so heavier molecules take a long time, and so you can actually do it that way. So with this, you don't have this like bending. Actually, you just use a highly accurate clock and stuff like that, and so you get very accurate measurements on biological samples. And so MALDI TOF or Electrospray TOF, those are the big ones. So like that. And so if you look at here, you've got chicken egg white lysozyme, which is the major component of chicken eggs. Lysozyme goes in and actually it's designed to bust apart cells, right? So it helps. It's actually sort of like an antibiotic within the cells, stuff like that. So if a germ gets in there, right, they're going to be a lot of lysozyme to break it open, and so it'll kill the cell. Unfortunately, Salmonella has figured out a way to avoid be resistant to lysozyme, so this way you can sometimes have Salmonella poisoning. But it's 14.3 kilodaltons, so it's 14,300. But if you look here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures, right? So not only have the 14,307, you also have 4 significant. You also have 4 decimal points too. Now, this is what would happen if you had 1 charge on it, right? If it were to pick up two hydrogens, right? You would actually it would go twice as fast, and so it would be accounted for half the speed, right, or half the size because it can go twice as fast. So like that, and if it picked up 3, it would go 3 times as fast, and so this. But you can sort of account for that, right? So like that. So also sometimes what will happen is your samples, 2 of the proteins themselves will glob together, and then it'll get a positive charge, and then it'll go half. It'll go half the speed, right? And so you pick it up here, but this is just 2 of them glob together, and so you get a dimer here, and then your proteins. But I mean, this is for something this large. For 14,000, you can get a really, really highly accurate mass. So it's pretty amazing component. But the nice thing is you don't see this fragmentation issue, something like that, which is nice. Okay, moving along, stuff like that. So we're going to talk about infrared spectroscopy next. And so it's particularly, we're going to be shining this light in this infrared portion of the spectrum at our samples and seeing what happens. Okay, so just as a reminder, so wavelength goes from peak to peak, right? So amplitude is from the mid to up to the peak, but the big thing we're going to talk about is peak to peak. So like that, and just as a reminder, the shorter the wavelength, right, the higher the energy, right? It takes more energy to make a short wavelength piece than it is a long wavelength piece, right? So that's why radio waves, they're really, really long, they're really low energy, and that's why we don't get cancer when we drive our car, right, with the radio on. So about that. So but if you're hitting X-rays, right, they're very short wavelength, and those will give you cancer too much because they're very, very high energy photons. So about that. But just there's an inverse relationship between mass and or not mass, energy and wavelength, right? So shorter wavelength, more energy. Okay, so this is what the spectrum looks like, and what we're saying is the and so we're going from. We look at wave numbers, which is basically a nice way of getting more comprehensible or more easier numbers to think about as opposed to a bunch of decimal places. So wave numbers, which we'll talk about in a minute, is actually just inversion. It's the inverted or reciprocal of the wave length, stuff like that. So what we're looking at is the sample. When you at this point here, what we're looking at is transmittance. Is how much of this light gets through the sample, right? So you have your sample, you're shining light at it, okay? And we're putting a bunch of different wavelengths through it, right? So in here, at this, say 4,000 wave numbers, the light goes all the way through, okay? But as the sample goes, gets into different wavelengths as it's going along, part of that molecule is going to absorb that light, okay? Specific parts of the molecule are going to absorb the light. And so what you're looking at is as it's going down, right? That's where the peak is, right? So it's sort of inverted, okay? So this means nothing's going through. This means everything is getting absorbed, okay? And so you're coming down here, and this is absorbed, that's absorbed, that's absorbed, and like that, okay? And so with that, so it's sort of inverted from what you would think about, right? So this is the important peak here at 3,400, and we sort of look at the maximum part of the peak, right? There's peak here, peaks here, peak here, and there's kind of something going on right there, but I'm not sure what's going on there. Something's happening, something like that, but it's absorbing the light too. Okay, so and again, we're talking about the infrared spectrum in here, right? And wavelength is just a wave number is 1 over the wavelength, right? So instead of having, instead of having a wavelength of 0.025. Right, so at that, what they're going to say is, we're going to be at 400. This is just an easier number to kind of wrap your brain around, right? So 4,000 is over here, 400 is over here, and it also sort of lets you think about the fact that 4,000 is higher energy than 400. It's also able to sort of, it's easier to think about, right? So high energy, big wave number, low energy, low wave number, right? So it's a way to do that. Stuff like this. So now is what used to happen is it used to be on a roller, and the roll used to go, and there used to be a pen that as it went by, it would draw like this, right? So it would, as the wave number went by, it would literally be a pen on there. Now with computers, you hit it all with all of the wavelengths at the same time, and then the computer can figure it out, something like that. So. Okay, so what's actually going on? It turns out that, molecules, we think of like the ball and stick, stuff like that, but that's actually not what's going on. Right? They're always wiggling, right? So if you've ever tried to hold a 2-year-old, they're always wiggling. Same thing with molecules, right? So you get the bond stretching, so bonds are going like this, they're going like that, they're going like this, they're going all sorts of crazy ways. Okay, but the easiest thing to think about this is that, that wavelength is going to be very distinct for what those two atoms are, okay, and how they're held together. So the easiest way to think about this is that if you're on a swing, right, you can't just randomly hit somebody with a swing and expect them to get higher and higher and higher, right? You have to hit a very specific rhythm in order for you to go higher and higher, right? So with that same thing going here, when it gets that particular rhythm, that thing is bouncing back and forth, that is vibrating back and forth, it gets absorbed. Okay, that particular wavelength gets absorbed. And that's characteristic of what the bond is wiggling at, and each one's gonna be different. Okay, so like that. And so what happens is you get this chart, right? So like that. So here's the chart here. I don't see it. Here's the chart here. right? So you are going to need to know this chart, know how to use this chart. You do not need to memorize this, okay? I don't know why people insist on having you guys memorize this, because nobody has. Those who haven't memorized are the ones that use it all the time, and they need it. Everybody else, what they do is they either just look it up, or they have a chart like this hanging on their board next to their desk, stuff like that. So I'm going to give you this chart. You're going to need to know how to use it, okay? And so what you need to do is to look at what is there, okay? So if you have, right, you're always going to have a CH bond. You're always a CH bond. You're always going to have a CC bond, CC single bond. Okay, those things are always going to be there, right? Because we're dealing with organic molecules. Okay, so what we're dealing with is all the other ones. Okay, so if you have, right? So if you have a compound, right? So if you have, and we'll talk about this. If you have the differences of saying you have both, say both the alkyne, right? There's a carbon-carbon triple bond, that stretch, but there's also the CH stretch off of an alkyne, and it's going to make a difference for how the molecule is put together, whether it has both of these or one. Okay, so you have to figure out what's there and what's not there. Those are both equally important. Okay, so what's going to happen is you're going to say, okay, we have a spectrum here, okay, and we have a bottle, and we think it's either one of these three, right? We don't want to go to mass spec is broken, so we can't do that because the mass is going to be a little bit different for each one of these. They're going to be off by 2, stuff like that. So we're going to use the IR because it's easier to use. We have one of that in our lab. You don't have to walk across the campus to use the mass spec or whatever. So what we're going to do is we're going to say, okay, we're going to look at these peaks, and we're going to say, okay, the hexane peak is only going to have CH and CC bonds, right? That's all it's going to have, right? But all these guys are going to have that too. Okay, but this guy here, the 1-hexene, it's going to have alkene peaks. Not only the CC double bond peak, which would be at about 60, it's going to be somewhere in this range. Okay, now this is an absolute, but this is close, right? So it will be about 1650, right? Which would be, right? Which is about 1650, which would be about here. Ooh, that's looking good, right? And then there should also be the CH peak coming off of the alkene, which is coming right around 3100, which would be right about there. Ooh, that's looking good. Okay, so we're looking like it's got those two peaks. Okay, that we would see. Now, just as a double check, so it's probably going to be this one, the hexene. But we do need to look at the hexine, right? Because this one, we would have the alkyne peak, a CC triple bond peak, which would be right around 2122, which would be right in here, and there isn't anything, right? It's all up at the baseline, which is up here, right? So there's nothing here, okay? And then also there could potentially be, right, because there's a hydrogen sticking off of here. There could also be one at 3300, which would be right there, which is nope, we don't have that. And so what's happening is, right? So we have this peak and this peak here. Okay, and so you can look at what are the differences between these, right? They're going to have slightly different fingerprints because they have slightly different stretches, right? Something like that. So, oh, I also should point out, I don't really necessarily care about the intensity. I'm looking at functional group and the absorption, okay? Because this can be dependent on the molecule. So I wouldn't get too worked up over the intensity. It's really this and this that are the issue that you need to know how to use. Okay, so again, at that. Okay, so here's the question. Okay, so we look at this, we say, okay, here we go. So we've got, what do we have? Okay, so we have a peak at 1150. Okay, so what could that be? Okay, so we look at our chart. Okay, we have a peak at 3400. Okay, so 1150, we're sort of going along here. We say, oh, it could be this here, right? So it could be that. Okay, so it could be a CO peak, right? Or a CO stretch, right? It could also be a CN, right? So if you just look at the numbers, right, it could be in there. Okay, right, and nothing else makes what's in there. So how about the 3400? Well, it could be here. Right, the OH, right? or it could be this NH here. But which set is it? Okay, it has to be this one right here, right? It can't be that. Why? Well, there's no nitrogen in the compound, right? I gave you the formula, C4H8O, right? And so we know it has to be these two. It can't be these guys, right? Because that doesn't make, because it doesn't make any sense by the formula. Okay, and so again, you have to think about what's there, what information is given and what's not. Okay, so here we go. So DOU, right? So we know it has that in there, right? So this is right. So this is a CO, and this is an OH. Okay, so we have to count for that for our structure, right? So here we go. So DOU, right, is equal to 2 times the number of carbons, which is 4 plus 2. There's no nitrogens, right? No halides, and 8 hydrogens, right? All divided by 2, right? So it's 10 minus the 10 minus 8, right? 2, right? So we 2 over 2 equals 1. Now the question is, right? So this is, right? So remember, this is pi bonds, right, plus rings, right? So this is equal to 1. Okay, so we have 1 degree of saturation. So we know we have an alcohol, right? So that's not going to be part of the degree of saturation. Okay, so how do we know? Do we know if it's a ring or a pi bond? Well, actually, so let's say the structure looked like 1, 2, 3, 4, 5. Let's say it was this, and then we had a double bond over here. Okay, notice what's missing, right? So we have spectrum for this. If it were a pi bond, right, what would we need? We'd need spectrum from this. This would give an IR signal too. Okay, we don't have that. Okay, we don't have the double bond. Okay, so that's not in this list, right? It's missing, right? So that means we cannot have the double bond. Okay, so that means we can't have a double bond in there, right? Or else it would be listed. So that means that all we have is a ring. Okay, so it has to look like this. So the easiest one is this, right? A 4-carbon ring with an alcohol coming on it. But in theory, you could also do OH, right? That gives you the right formula. Or you could do, you could do that. Okay, but it can't give this. Okay, why? Because we don't have those the correct signals to make sense. These would give it to you, right? Now, again, CC bonds, single bonds, I'm not going to write those on there because those are always going to be there. CH bonds, always going to be there of alkanes. Okay, but you have to figure out what's there and what's not. Okay. Next up. Okay, so we look at what's here, right? So same formula, right? But we have one at 1750. Okay, so we sort of go in here, right? We look in here, and, oh, here we go. It has a ketone in it. Okay, so this we know is a ketone. Okay, right? So the DOU, right, is what? 2 times 4 plus 2 plus 0 minus 0 minus 8, right? Right, we figured out that that's 1. All right, so this is, right, so that's pi bonds plus rings. So what is it? It has to be the pi bond. Why? Right? Because a ketone, remember, is C bond O, right? There's a pi bond here. It doesn't necessarily have to be a carbon-carbon pi bond. It just has to be some sort of pi bond, right? So here, this one, we have this one as the ketone, and that's the only one. We only have one, right? And that ketone counts for it. Okay, so the molecule has to look like this, and that's the only structure it could be. Now you could do 4 and put the OH there, or the CO there, but it's the same molecule, right? But this is the only thing it could be that satisfies both this formula and this infrared spectrum. Okay, so be careful. Okay, and that's it. So good luck.